Hello everyone, and welcome to another DIADEM Elite tutorial. In this video, we will be covering DIADEM Elite's graphing window. The graphing window is an extremely powerful tool that allows you to identify trends between chemicals and properties, validate whether the results of a prediction method might be reasonable, and much more. Graphing interfaces also appear in the comparisons window and the predictions window. Understanding the graphing window will help you to use these tools much more effectively. To open the graphing window, click the Graphing button in the sidebar of DIADEM Elite. The window will open on a Select Compound screen, similar to the main window. To use the graphing window, you will need to select one or more chemicals. For the purposes of this tutorial, we will use methane, ethane, and propane. Now we can choose whether we want to graph constant properties or temperature-dependent properties. We will first look at constant properties. Navigate to the sidebar on the left side of the window, then click Const Properties. We can now see the Constant Properties graphing menu. On the far right of the screen is the Constant Properties graph. It has a legend on its right indicating which colored points correspond to which chemical. The selected properties and units are displayed next to the X and Y axes, respectively. By default, the graphing window initially displays a graph of molecular weight on the x-axis versus molecular weight on the y-axis. In the bottom of the window, we can see a large gray box that reads Selected Data Point Details. If we click on a point in the graph, like the point representing ethane's molecular weight, details about the data point will fill in that box as shown. These details include the source of the data, the uncertainty of that data point, the date the point was recorded, and more. To the left of the graph is a control panel interface. This interface allows us to manipulate the graph on the right, letting us see more useful graphs than molecular weight versus molecular weight. For each axis, we can change which property we are plotting by selecting the property dropdown, like so, and then selecting the appropriate property, in this case, critical volume. Now we have a graph of molecular weight on the y-axis versus critical volume on the x-axis. We can also change the format of an axis by graphing the data linearly, graphing the logarithm of the data in base 10 or the natural base, graphing the inverse of the data, or by graphing the number of carbons on the x-axis. These options are useful ways to linearize complex plots and can sometimes reveal relationships that are not obvious at first glance. If we want to change the units of an axis, we can select the desired units from the Units drop-down menu. For properties where this is relevant, such as heat of formation, DIADEM also offers both molar and mass units. Now let's scroll down on the control panel. As we do so, several new configuration options are revealed: Data Selection, Tools, and Save Plot. The Data Selection option lets us choose which data points to show in the graph. By default, only accepted points are shown. However, we can also choose to include rejected, unevaluated, and not used data points, as shown here. This can be a useful tool for data evaluation. However, for more complex chemicals with more data points, it can also cause the graph to become quite cluttered. To remove points, click All Data to clear the graph. Then select the data types you want to include. We'll return to just accepted data points. We can also remove specific points from the graph by clicking on their entry in the legend, like so. Click on one of the points to return it to the graph. Double-clicking on a point in the legend will remove all other points, as shown. Double-clicking on that point again will restore the other points. If we want to hide the legend itself, we can do so by clicking Hide Legend in the Tools option. Once we hide the legend, the button changes to Show Legend, which can be clicked to restore the legend. If you want to zoom in on a part of the graph, click and drag a selection across the graph window, like so. Your selection will be set to the new boundaries on the graph. To navigate around the graph while zoomed in, you can click and drag on the x-axis to move left and right, like shown. Or you can click on the left y-axis and drag on it to move up and down, like so. To further rescale the graph, you can click and drag on any of the bottom corners of the graph, like so. To return to the default scale, double-click on the graphing window like so. If you want to see the numbers associated with a point, you can simply hover over the desired point and the number will appear, along with a small amount of information on the source and which chemical the point refers to. Lastly, if you are a Dipper sponsor, you can export your plot by clicking Save PNG, Save JPEG, or Save SVG. Doing so will export an image in the chosen file format. Now let's look at an example of the power of the graphing tool. To do so, we will need more compounds than just methane, ethane, and propane. Here is a graphing window containing all the members of the N-alkane family of chemicals that Dipper has data on. As you can see, the y-axis property is now critical pressure, and the x-axis property is molecular weight. There is a clear trend in the data here. If I change the y-axis scale to 1 over y, the trend suddenly becomes much clearer. Critical pressure is inversely proportional to molecular weight in N-alkanes. The graphing window is extremely useful for identifying potential relationships like this for further analysis, which makes it easier to validate the results of a prediction tool. Now we will return to our initial 3 chemicals and show how to use the graphing window to analyze temperature-dependent properties. To access TDEP property graphing, we click on the TDEP Properties button in the sidebar. As soon as we do, we can immediately notice several differences between TDEP property graphs and constant property graphs. The first is that we can no longer change the property that appears on the x-axis of the graph, which is reserved for temperature. However, just like before, we can change the scale and units of the x and y-axes as we desire. Instead of carbon count, the x-axis now has the option to be rescaled by reduced temperature by clicking on TR like so. If we scroll down on the control panel, we see options that are similar to those in the Constant Properties tab. The data selection feature functions the same way as it did when graphing constant properties, allowing the user to select which types of data they want displayed in a graph. The Save Plot options are also identical to those in the Constant Properties tab, allowing the user to export the graph they've generated as a JPEG, PNG, or SVG file. The Tools tab Hide Legend function works identically to the way it did in the Constant Properties tab, allowing you to hide and re-show the legend. The new addition of a Vapor Pressure Format button allows you to automatically format the graph in the form of the natural log of your desired property versus the inverse of temperature. Just like before, if we click on a point, we can see additional data about the set that it comes from, rather than the point itself, as well as information on the rest of the points in the set. We can see similar information by clicking on a solid line, which represents a correlation. This will display metadata about the correlation. If we only want to see a subset of the correlation line, we can change the plot from values to something within its minimum and maximum temperature range. Let's show 100 to 200 Kelvin. As you can see, this causes a significant portion of the correlation to not be shown on the graph. If we want to go back to our full bounds, we can simply enter the minimum and maximum temperature ranges listed below. Now we have restored our full correlation. If you would like to see how well a correlation extrapolates beyond its temperature range, you can also enter values into the correlation details boxes beyond the correlation's minimum and maximum temperature. However, these values should be used with caution, as Dipper does not recommend using correlation values from outside the temperature range. Just as before, if we want to specify which points we want to see, we can click on their element in the legend to hide the set corresponding to a point, and click it again to bring it back, or click on the line corresponding to a correlation to hide it, and then click it again to bring it back. Double-clicking on an element will isolate it, showing only it and removing all other sets from the graph. Double-clicking on it again will restore the original view. Once you have isolated an element on the graph, you can also click on other legend elements to add them individually to the graph, allowing you to hand select the data and correlations that you want to view at any given time. To restore the original view, double-click on a legend element to isolate it, then double-click again to bring everything back to the graph. Scaling, navigation, and zooming also work the same way as they do in the Constant Properties tab. If we want to zoom in, just as we do there, we click and drag on a selection of the graph, and can navigate by clicking and dragging on the X and Y axes to move left and right and up and down respectively. We can also further rescale the graph by clicking and dragging on the bottom corners, as shown. We can restore the original view by double-clicking. Now that we have covered the main features of the graphing window, we will move on to showing you how to access graphing window functionality from the predictions and comparisons windows. The predictions window contains a built-in graphing tool that can be used to compare prediction results with accepted property values. This feature is useful for checking to see how well a certain method of prediction fares when used on a family of chemicals. For more information on how to use the other features of the prediction window, refer to our prediction window tutorial linked below. To access the predictions graphing tool, open a new predictions window. Select the compounds you would like to run predictions on. As before, for the purposes of this tutorial, we will be using methane, ethane, and propane for this demonstration. Select Predict, then choose the property you would like to make a prediction for. In this case, we'll do critical pressure using the Ambrose PC method. Click Predict Property. Once the prediction method finishes and its results are shown in the Prediction Results window, click Graph Results. A new graphing tool window will appear, with the results of the prediction shown as triangles and the data points themselves shown as circles. As you can see, there's some significant variation in how well the Ambrose PC method predicts the critical pressure of these compounds. The graphing tool allows you to see this variation. As of May 22, 2025, the predictions graphing tool is slightly bugged and currently freezes if you try to graph the results of 2 or more prediction methods at once. The graph will still render, however you will be unable to interact with the window in any way other than to close it. Exercise caution when trying to graph the results of multiple prediction methods. Additionally, graphing from Smiles predictions does not work yet either. The Comparisons tool also contains a built-in graphing window, which allows you to visually compare the properties of different compounds. For more information on the other functions of the Comparisons tool, refer to our Comparisons tool tutorial linked below. To access the Comparisons graphing window, first open a new Comparisons window, then search for the compounds you wish to compare. In this case, we will continue to use ethane, methane, and propane as our example chemicals. Click on Const Properties or TDEP Properties depending on what you wish to compare. In this case, we will compare constant properties. Once the window has loaded, select the property you want to compare. For this example, we will compare heats of combustion. Now select Graph Compounds to display a Comparisons graphing window. This window functions identically to the normal graphing window and is simply included here in Comparisons for convenience.
Now it's time for a DIADEM demo. Let's use what we've learned about the graphing window to come up with a solution to a specific problem. In this scenario, let's imagine we're a benchtop chemist working with benzyl methacrylate, a monomer used for polymerization. We'd like to dissolve a portion of it into a liquid so we can study the kinetics behind its polymerization behavior. To do so, we'll need a relatively safe solvent to work with. I've prepared a list of 80 prospective solvents using an advanced search in DIADEM Elite, something we'll cover in a future video, and would like to narrow this down to a few prospective candidates to help get a jumpstart on research. To save time, I've loaded these chemicals into the graphing window beforehand. As you can see, the graph is on the default screen of molecular weight versus molecular weight. To select a solvent, we want to find a compound with a solubility parameter relatively similar to that of benzyl methacrylate. Let's put solubility parameter on the y-axis and see what ends up where. To do so, click the property dropdown, scroll down to solubility parameter, and select it. We would also like the chemical we choose to use as our solvent to not be particularly flammable, so let's put flashpoint on the x-axis. Here we are. As you can see, we now have a graph of solubility parameter versus flash point. To make it a little easier to compare compounds, let's change the units on our solubility parameter to be in square root cals per centimeter cubed. Now we have a nicer scale. Let's try to find benzyl methacrylate on the graph. As you can see in the legend, it is green. If we click this point to make the point disappear, we can see this point here vanishes. So this is how we can find benzyl methacrylate. As we can see, it's in between 9.6 and 9.7 square root calories per cubic centimeter. So let's zoom in on this portion by clicking and dragging on the graph and see what other chemicals have clustered around it. Here's what we have so far. As you can see, we're in a nice flashpoint range, so all of these chemicals should be reasonably safe if we're performing this operation at room temperature. Let's see what's close by. We have several chlorinated compounds, some large glycol compounds, some large ethers, more chlorinated compounds, another methacrylate, and benzyl methacrylate here. From a little bit of prior research, I know that this compound, diacetone alcohol, is a relatively common solvent. Now I can see that it's close to the solubility parameter of benzyl methacrylate, so I suspect that it will work as a solvent. And I have a lead on further research that I can do to choose the best solvent for this kinetic study. That's all for this Dipper demo and for this tutorial video. We hope that you have enjoyed and that you've learned what you needed to about how to use the graphing window most effectively to help you in your engineering design work. Thank you so much for watching. And as always, feel free to reach out to us on Zendesk at support@dipper.byu.edu with any questions. Thank you so much, and we'll see you next time.